Okay. So in last lecture we discussed about the molecular orbital diagram of C2 molecule. Now in this lecture we have to discuss about the construction of molecular orbital diagram of O2 molecule. Okay. So as we know that first of all we have to write down the electronic configuration of O2 molecule. So we know that oxygen is having atomic number is how much it is atomic number? Yes, it is an 8. Okay, so oxygen is having 8 atomic number, okay, and whose electronic configuration is nothing but 1s2, 2s2 and 2p4. Okay, so means total 8 electrons are present in one oxygen atom, and collectively we have say 8 plus 8 means that is 16 electrons in two oxygen atoms. Okay, so what happened here, we have three types of atomic orbitals, that is 1s, then 2s and then 2p orbital. Okay, but as we know that while constructing the molecular orbital diagram of such type of element which having suppose three orbitals, so we can consider this 1s orbital as a non-bonded. Okay, and instead of this we can write down only kk. So furthermore, say when the 2s orbital of one oxygen is combined or interacted with the 2s orbital of the another oxygen according to the LC approximation, they can form two molecular orbitals. The first one is nothing but say the sigma 2s, okay, which is bonding one, okay, having less energy, and another is nothing but the sigma star 2s, which is called as the anti-bonding molecular orbital, formed due to the repulsion of the AOs, okay, and having comparatively higher energy. Similarly, here we have what say the p orbital, such as what this is p orbital, that is what px, py, and pz, which containing four electrons. And similarly, on other sides, we also have the same condition. Okay, so collectively we have what a six atomic orbitals. When they undergo the LC approximation, we got what say the six molecular orbitals, out of which half of this means the three orbitals are bonding molecular orbitals, okay, having less energy because they can be formed due to the attraction of the EOs, okay, and half of that are anti-bonding molecular orbitals formed due to the repulsion of the EOs and having higher energy. So here, when what say the px orbital means what this is 2px is combined with what say the 2px orbitals over here. Here we have what say the z orbital, means that is what say the 2pz and 2pz. They are reacted. Okay, means they can be interacted via say the internuclear axis overlapping. So they can form a sigma bond. Okay, so this is nothing but said to be the sigma orbital. Okay, so it is nothing but said to be the sigma 2pz. Okay, sigma 2pz, and this one is nothing but said to be their anti-bonding molecular orbital called as what say the sigma star 2pz. So these are nothing but said to be the two sigma orbitals, means that is bonding, and this one is anti-bonding molecular orbital formed due to the combination of the 2pz molecular orbital. Okay, and they can interact it through the internuclear axis overlapping, so that we got this sigma orbital. Remaining two means 2px and 2py. So 2px and 2py orbitals of both oxygen atoms, so they combine, okay, according to the LC approximation, and they got what say the four molecular orbitals. Okay, so their interaction is nothing but the you can say that lateral overlapping is there or a sidewise overlapping is there. That's why we got to the four pi orbitals. Okay, namely they are called as what say the pi 2px, pi 2py. Okay, these are nothing but said to be the bonding orbitals formed due to the attraction of the EOs having less energy. And another is nothing but said to be this pi star 2py, pi star 2p, pi star 2px, pi star 2py. These are nothing but the anti-bonding molecular orbital formed due to the repulsion of the EOs. Okay, so this is nothing but said to be the construction of the molecular orbital diagram for O2 molecule. So now comparatively this diagram looks like this. Okay, this is an energy axis which is vertically upward. Okay, this one is the atomic orbitals, okay, of oxygen atom, one oxygen atom. This is atomic orbitals of the another oxygen atom, and this is nothing but the molecular orbitals of what say the O2 molecule. Now after the construction of this molecular orbital diagram, we have to write down the MO electronic configuration of O2 molecule. Okay, so how to write down this? You just look towards it. Okay, So first of all, we have to write down what's the kk. So what is kk here? Here we write down what's the kk. So what is kk? Kk is nothing but say they can show the non-bonded electrons or orbitals, non-bonded electrons of what say the 1s and 1s orbital. Okay, so we are write down here kk. So k for what? 1s orbital of one oxygen, and this k is for 1s orbital of the another oxygen atom. So here we write down what the kk. Next is nothing but said to be it is an sigma 2 yes, okay, sigma 2s which having two electrons. So we can write down what sigma 2s2, here sigma star 2s2, here we can write down sigma 2pz2, here we can write down what pi 2px2, pi 2py2, okay, and here we can write down what say the pi star 2px1, pi star 2py 1. Okay, so these are nothing but said to be the electronic MO electronic configuration of O2 molecule. So it can be it is very easy to write down from what say the molecular orbital diagram. You just observe it and you can write down it. Means you can write down what say the orbital and the number of electrons in superscript. Okay, so in this way you are you try to you can write down what's the MO electronic configuration of O2 molecule. Now we talk about what say the magnetic behavior of O2 molecule. So we know that at the very first slide of this lecture, okay, or this unit, we are talking about what say the VBT fails to explain the paramagnetic nature of O2 molecule. Okay, so the explanation will be here. Here in case of this diagram, okay, when we observe say the molecular orbitals, okay, bonding as well as anti-bonding, so we observe that here we have a two unpaired electrons present in this anti-bonding molecular orbital, that is pi star 2px and pi star 2py. So due to the presence of this unpaired electrons, okay, this molecule is a paramagnetic in nature. Okay, paramagnetic in nature. So there is a correction. Okay, so this molecule is what paramagnetic in nature due to the presence of the unpaired electron in pi star 2px and pi star 2py. So we have to write down here what due to the presence of the unpaired electrons in these orbitals, that molecule is paramagnetic in nature. Next is nothing but our final point is to calculate the bond order. Okay, so how to calculate the bond order? So it is very easy. Many times I will told you the formula for the calculation of the bond order. It is an half into the number of electrons present in the bonding molecular orbital minus number of electrons present in the anti-bonding molecular orbital. So let's we count the number of electrons in say the bonding molecular orbital. So it should be 2. It is present in the sigma 2s. Okay, so it is 2. Then this one, it is what sigma 2pz, this 2 plus 2 4, and here this is what pi 2py, pi 2px, pi 2py. So here we have what 4 electrons. So totally we have what 2 plus 2, and that are 4, and 4 plus 4, that is what 8 electrons in 8 electrons in, you can say that in bonding molecular orbital. So we can place this 8 over here. Okay, minus number of electrons in ABMO. So let's we count. So here in sigma star 2s orbitals we have what 2 electrons. Okay, and here in pi star 2px and pi star 2py we have 2 electrons. So the 2 plus 2 is 4. We will place this 4 over here. So they are what, say the 8 minus 4. So the answer after the calculations we got what, say the bond order must be 2. It means that in oxygen molecule, there are you can say that there are two bonds. Okay, means first one is nothing but said to be the sigma bond, another is nothing but the pi bond. So two bonds are say present in our O2 molecule. Okay, and that's why the bond order should be 2. Okay, so this is all about what's the construction of the molecular orbital diagram of O2 molecule. So what we have to do, we have to first we have to write down the electronic configuration of O2 molecule. Then we have to write down what, say instead of say the 1s orbital, combination of the 1s orbital, we can write down kk. Then 2s will combine, we got two molecular orbitals, that is what sigma 2s, this one sigma 2s, and then one sigma star 2s. Okay, then when 2p orbitals, okay, so the 2p orbitals will combine, we got what 6 molecular orbitals, out of which 2 are sigma, is this one sigma orbital, that is what bonding and anti-bonding, is this one sigma 2pz. and sigma star 2pz. These are what sigma orbitals formed by the internuclear axis overlapping. Another four are nothing but said to be the pi orbitals, which are formed by the lateral overlapping of the p orbital. So here, in case of what, two are what bonding, and another two are nothing but the anti-bonding. So collectively three are bonding orbitals, collectively three are nothing but say the anti-bonding molecular orbitals. So here is nothing but said to be the pi star to p x and pi star to p y. They contain the unpaired electrons, so that the molecule is paramagnetic in nature. And when we count the bond order, so it should become two. Okay, so in case of what oxygens, we have double bond in between them. Okay, so this is all about O2 molecule. Now we move towards our next molecule. Okay, so here the next molecular orbital diagram is associated with the O2 positive molecule. Okay, O2 positive. So see, what is O2 positive? So the O2 positive is nothing but said to be when we eject one electron from what say the O2 molecule. Okay, so we got what say the O2 positive molecule. Okay, so see, this is an oxidation process, means where we eject one electron from say the O2 molecule. Okay, so now we have to write down what say the electronic configuration first. So first we have to write down what oxygen 8, okay, is equals to 1s2, 2s2, and 2p4. Okay, 2p4. Then next is nothing but next oxygen. We have one electron less in this molecule, so we can write down another oxygen which having electronic configuration 1s2, 2s2, and 2p3. Okay, so we have to write down one less electron over here. Why? Because this system contains only 15 electrons. Okay, so yeah, this diagram is somewhat different because there is a correction. Okay, see here we have what 4 electrons, but we have to show only 3 electrons over here. Okay, there is a mistake in this orbital, so I will tell you. Okay, so next what happened when we combine what's the 1s orbital, so instead of this we can write down only kk. Okay, we are not going to show this. Okay, so instead of this, when these two orbitals are combined, so we have to write down kk over here. Okay, in between these two orbitals. So this is an case. Okay, another is nothing but said to be say this 2s, and when 2s orbital is combined of both oxygen atoms, we got what 2 molecular orbitals, same as that of what say the O2 molecule. So this first one is bonding is nothing but say the sigma 2s, and another is nothing but the sigma star 2s. Okay, then finally when 2p orbitals are combined, so we know that when 2pz and another 2pz, they are overlap on the internuclear axis, they can form two sigma orbitals. That is what first is bonding, that is called as the sigma 2pz. Another is anti-bonding, that will be called as the sigma star 2pz. Okay, and remaining 4 orbitals means here px py and there px py, they can combine laterally. Okay, so they can form pi bond. Okay, so we have what 4 pi orbitals over here. This is what say the pi to py, pi to py, pi to px. Okay, this is what say the pi star to py, pi star to px. Okay, so now we have to say we have to fill up the electrons. So how many electrons in O2 positive molecule? So obviously 15 electrons we have. So how to put this electron? So about kk we forget about kk. Okay, so 2 electrons over here, 2 electrons over here. So we do not talk about these electrons. So this is nothing but said to be the 2 electrons, and other is what 2 electrons, and here is nothing but 2 electrons, and this orbital also contains about 4 electrons. So when we calculate this electron, so it should be what 4 plus 4 8, okay, 9 10, and these are nothing but said to be the 14 electrons, and 1 electron remaining is placed in what say the pi star to py. Okay, and this pi star to px is nothing but remains vacant. So this is nothing but the case. Okay, so difference in between what say the O2 positive molecule is that, so that this diagram contain one less electron as compared to the O2 molecule. Okay, just means in case of what say the O2 molecules, we have electron over here. Okay, and in this molecules we don't have electron over here. Pi, because it is nothing but the oxidation product of the O2 molecule. So that's why we have one less electron as compared to the O2. O2 molecule contains 16 electron. O2 positive molecule contain only 15 electrons. So this is nothing but said to be the case. Now we talk about what's the MO electronic configuration. So it should be what kk. Here what sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2py, 2 pi to p x2, okay, then pi star 2 p y 1 equals to pi star 2 p x0. So this is nothing but the MO electronic configuration of this molecule. Now we talk about what's the magnetic properties. So here we know that we still have one unpaired electron. So that's why this molecule is paramagnetic in nature. So whenever we award say the unpaired electrons in such systems, so that molecule or that system is said to be paramagnetic in nature. If all electrons are paired, so obviously this system is what's the diamagnetic. Okay, and when we calculate what's the bond order, so when we place what's in the bonding electrons, so how many bonding electrons we have? 2 plus 2, okay, and this 6, okay, so 6 plus 4 is nothing but 10, so we can place 10 over here, minus 5, so 5 is what? These two, that 2, and this one, so 5 electrons. So bond order came to what? 2.5. Okay, means what? These O2 positive molecules, they having what said to be the 2.5 bond in between them. It means what? It is more stable as compared to what's the O2 molecule. Okay, O2 molecule, because in case of the O2 molecules we have only 2 bond, okay, double bond, but here we have 2.5. Okay, means 2.5 bond is there. Okay, so that's why this molecule is more stable. So see what, as we eject the electron from the O2 molecule, okay, so that electrons present in the antibonding molecular orbital, so we can eject it. Okay, so their bond order must be increased. Okay, it's about say about O2 we have a 2 bond order, but when we eject one electron we got what? The O2 positive molecule, so that molecule is having a 2.5 bond order, so it is what more stable as compared to say O2. Then we move towards what our next molecule. Yeah, that is what O2 negative. So it is nothing but the reduction product of the O2 molecule. So how? Means when we add one electron to the O2 molecule, so that will be the O2 negative. Okay, and that negative charge shows the addition of one electron. Okay, negative charge can show what's the addition of electron, positive charge can show the ejection of the electron. So here we can write down what say how to write down the MO electronic configuration, or say the MO diagram of this molecule. So here in case of what say the O2, we have I think there is a correction in between what this diagram. Okay, so we have what we have in O2. So total number of electrons in systems are nothing but said to be 70. Why? Because you compare with what's the O2 molecule. In case of the O2 molecules, we have what? 16 electron. Okay, 16 electrons. So here we have one more electron, so that will be the 17 electron. Okay, so how to write down this? So first we write down what? O8 electronic configuration is what? 1s2, 2s2, 2p4. Another oxygen we have to write down O9. Okay, means you can just write down O. Electronic configuration should be what? 1s2, 2s2, and 2p5. Okay, 2p5, because we have one more unpaired electron. Then after about what was say the combination of the 1s 1s, so instead of this we can write down the kk. Okay, then we write down what say the combination of the 2s, means what 2s and 2s will combine, we got what? Sigma 2s and sigma star 2s. Okay, this is another present say notations, you forget about that. So here 2s and 2s will combine, we got what? 2 molecular orbitals, that is what? Sigma 2s and sigma star 2s, each contain 2 electron. Here we have what say the p orbital. So obviously the z orbitals, means here 2pz and 2pz, they overlap on the internuclear axis, and we got what say the sigma orbital. So that sigma orbital is nothing but said to be the sigma 2pz, and here is antibonding, what it is called as the sigma star 2pz. Okay, so these are what say the antibonding molecular orbitals. Okay, then remaining 2 and here 2 means 4 orbitals, they undergo the lateral overlapping, so they can form the pi orbital. We can write down like this. That is what say the pi to px and pi to py, each contain 2 electron, and here is what the pi star to px and pi star to py. Okay, so when we fill up the electron in such system, so what happen? Here we have what say the 17 electrons. Okay, so this is nothing but said to be the extra electrons as compared to the O2 molecule. Means totally we have what say the 17 electrons, and this is what say the extra electron. Okay, so see when we write down the MO electronic configuration of this system, so it should be first we write down the kk, and second is nothing but said to be the sigma 2s2. Okay, this one is what say the sigma 2s2, this is what sigma star 2s2, Okay, then what say the sigma 2p z2, then pi 2p x pi 2p y 4, okay, or 2 2. And here we have to write down what the pi star 2p x2 and pi star 2p y 1. Okay, so this is what say the MO electronic configuration of what say the O2 negative molecule. Next is what say the magnetic behavior. So as we already seen over here, there is an unpaired electron. There is a presence of the unpaired electrons here in the antibonding molecular orbital, make this molecule paramagnetic in nature. Okay, it is very easy to say that what whether it is what paramagnetic or diamagnetic. Just you observe the unpaired electron. If it is present, it is paramagnetic. No present, diamagnetic. And then finally we determine the bond order. So the bond order should be half into number of electrons in BMO minus ABMO. So it should be number of electrons in BMOs are nothing but 8. Okay, so how 8? Here what 6 electrons, and this is nothing but 2 electrons. So the 6 plus 2 is what A, and these are what say the 5 electrons, means 2 plus 2, 4 plus 1, that is what 5. 8 minus 5, it should be what 3. 3 by 2 is nothing but 1 by 5. So bond order is nothing but 1.5. Okay, so as the negative charge increases, the bond order should be decreases. Means in case of what the O2, we have a 2 bond order. In case of the O2 negative molecules, we have say bond order must be 1.5. Means it should be decreases by say to be the half and part. Okay, so this is all about what the molecular orbital diagram of O2 molecule. Now